correlation at first sounds different than a t-test, but in actuality, they're really the same thing, or they work the same way. Having said that, in correlation, we're interested in covariances. Well, what is a covariance? If we look at the formula for covariance, let's just look at the numerator here to start. We can see that if the difference between x1 or xi, any individual score, and the mean of x, if that difference is large and positive, and if the difference between y sub I or y1 or any individual score, if the difference between any individual y score and the mean of y is large and positive, then the numerator will also be large and positive. So this whole thing will become positive. You basically have a big positive difference here and a big positive difference here. You multiply them together and you get a big positive number. If the difference between x1 or x of I and the mean of x were large and negative, and the difference between y sub I and the mean of y is large and positive, then the numerator will be large and negative. Okay, so if this one's positive, if this one's very big on the positive side and this one's very negative on this side, then the top becomes a negative number. And if they're both negative, if they're both large and negative, then it becomes a positive number again. So this is repeated for every score, and then summed, and then scaled by the number of participants, the n being the number of participants, and you subtract by 1 for degrees of freedom, which is a little more of a complex topic. But for now, you just worry about it. You basically just average by the number of subjects. However, if we use the covariance for our test statistic, then every study would have its own units, the units of the variables used in the study. So if you're interested in money and happiness, then you would have some score that was some kind of combination of money and happiness. If you had happiness and brain signals, then you would have some kind of score that's a combination of happiness and brain signals, and they would all be at a different scale. Some would be in millivolts, and some would be in dollars, and some would be in happiness units, and it would be really hard to compare things across studies. Because of this, we standardize the covariance by the standard deviation for each variable. Here, we take this, the covariance, and we put it on top of the standard deviations. The correlation coefficient always lies between -1 and 1, with -1 and 1 indicating a perfect relationship. In this way, it does make it easy to compare across studies and across different units of measurement, because we're talking about the same thing. It's been scaled. Sometimes predictor variables are related to each other, and they're also related to the outcome variable. When we want to know what one variable specifically or uniquely predicts, we can conduct what's called a partial correlation. The partial correlation between x1 and y is depicted by the b. This is the variance that would be used to compute the partial correlation. It's the covariance that is shared by x1 and y that is not shared with x2. Put another way, b represents the relationship between x1 and y after statistically controlling for x2. That's what a partial correlation is. A semi-partial correlation is similar, but they're not often reported or computed in research studies. It's a bit like cheating, and it's not clear how much of C contributes to the effect. So if you did a semi-partial correlation, you would see the effect of x1 and y1 predicted by B and C. and it's never really clear how much C contributes to the effect in this case. Bottom line, take-home message is that stick with partial correlations. Don't bother with semi-partial correlations, but it's going to be good to know what a semi-partial correlation is. Notice the subtle difference in the conceptual formula for effect size here. Whereas the t-test told us how likely the difference in means is greater than 0. The effect size tells us how big the difference in means is. So we could have a big difference in means, but it may not be greater than 0. It may not be more than it may not be greater than we would expect given the sample means in our estimate of the population mean. Put another way, the effect size tells us how much of an effect can be attributed to a variable, or how much we can predict with another variable. Two common indicators of effect size are the correlation coefficient, which we saw, the R, Pearson's R, and as well as Cohen's D. The general interpretation of the magnitude of these effects is listed here. I gave you some guidelines. It's also in your text. These are only guidelines and should be interpreted in the context of your study. So these can mean different things depending on the study. In some cases, where every other report found an effect size of 0.1, and now you're reporting an effect size of 0.3, you may say that that's a large effect given that everybody else found a small one. And just depends on the context which you're reporting in your experiment. Okay, that's all for this week. Thank you.